Thank you all for coming. I appreciate you making the effort to come see some of the work that we're doing in North America and abroad. Our company, StructureCraft, we're both structural engineers and builders, and we're founded by my father, Gerald Epp. And given that this is the International Association of Bridge and Structural Engineering, in some ways he should be talking here about his incredible bridges, because he has designed some masterpieces in timber footbridges. And so he founded our company almost 30 years ago, and his vision was to kind of reconnect engineering and construction. And so I grew up kind of in our family of people looking at kind of design. My dad was kind of sketching at the kitchen table, and this was me when I think was, I don't know, 12 or 13, out learning how to run woodworking tools. And so our company, we work across North America and Asia. Starting to do a little bit in Europe, but not a huge amount. And we work on all types of buildings and structures, from long span roofs to bridges to office buildings, all sorts of interesting different structures, primarily with a bit of a focus on using wood as a structural material. But perhaps uniquely our team, because we're both engineers and builders, we have carpenters, we have installers, we have people who know how to run cranes. We have master craftsmen, and we have computational designers and engineers. So we have kind of this wide range of people who get involved all the way from conceptual design all the way through to manufacturing and construction. And so today I want to talk to you a little bit about, why do we want to kind of try to encourage a reconnection of design and construction. I think going back in time, of course, there didn't used to be that separation. And I love this quote from Georg Schleich, where he talks about labor cost outweighing material cost, and as a result, we maybe don't put as much effort into the structures that we design, or we're not given the fee or the budget to put that effort in. And so then what results, and what, if you look at our current building stock, results from the inability maybe to apply thinking as much as we perhaps used to. And so thinking about this a bit more, I started thinking about the interfaces that have arisen between us as everything good? Oh, okay, move it over. Okay, thank you. But the interfaces that have arisen between us as designers or constructors and the buildings that we build. And I remember when I first moved here to London, I think it was 2008, I went and saw a lecture by Bjarke Ingels, and he had this this is my first thinking about, okay, this is an interesting interface to think about design. Let's make it a cartoon, and let's communicate our designs through a series of almost cartoon-like diagrams. But of course, we construct many different interfaces between us and our designs. Maybe that's computational design tools like generative components or Grasshopper, or maybe it's finite element analysis for those of you who are structural engineers in the room. But this is my father again, kind of this direct connection between the human and the material. At the end of the day, what we are shaping are structures built out of raw materials. And so if we think about kind of us as designers back 6,000 years ago, this is in Mesopotamia, where you were shaping mud bricks with your raw hands to create your own house, right? And you had this kind of almost visceral connection between yourself as a builder or as a shaper of material and the buildings you were designing. And so if you did a bad job, well, you would, your building would leak, or you would have to deal with the consequences of your design. And so I think we learned by doing, and we had this intimate knowledge of materials, and there was really not a huge barrier between design and build. And of course, the first interface, perhaps, if you think that was constructed, was the drawing, and this idea of kind of abstracting design from the material feedback and starting to, draw our designs so that there could be this separation between design and builder. But actually the separation between design and builder didn't really occur until the Renaissance, because there's the architecton, right? The chief builder that kind of connected the design to the construction. But it allowed us, imagine, abstract, but it did remove this kind of immediacy of, say, material feedback. And so I think the next interface that arose was the module. And so we started kind of creating ways of partitioning space into these repeatable geometries. This is the Roman brick, right? And so the modules, I think, though, were beyond just a physical object. They were almost became like a shared understanding, which allowed knowledge, like construction knowledge or design knowledge, to travel. This is Trajan's markets. And but these modules, once they became entrenched in the supply chain, they became, designing outside of those norms became maybe a little more difficult. And so they gave us a structural design language, but in doing so, they started to shape what we say. And then I think about the next interface. So you have the drawing, the module, and then of course the calculation. We start with the Roman arch, and then we start to understand funicular shapes and vaults, and we have groin vaults, and we have all these incredible innovations in using geometry to achieve efficient structural forms. But as that kind of changed through time, we've kind of moved from these efficient geometries, haven't we, into rectangular beams, which are highly inefficient, and our groin vaults have turned into big, giant, flat slabs, haven't they? And so it's interesting how, although we have this incredible capability to calculate our structures, often the structures that we do build aren't as efficient, nearly as efficient as they actually could be. And so, the next interface I think about is the catalog. During the Industrial Revolution, the number of materials we have, the palette of materials we have to design with just exploded, right? In the age of wrought iron, you think about the word manufacturing. It literally comes from the Latin words manufacere or facere. I don't know exactly how to pronounce it, but those two words literally mean to make by hand, right? And now we look at manufacturing today, it's become mass production by machines, right? And so the craft and the amount of detail and ornateness that we see. I was looking through some of the train stations as I was traveling around London for the last 2 days, and the incredible ability to kind of shape raw material, even metal. Like today, we got shear tabs and bolts, don't we, for metal? We don't have the intricacy and the beauty of some of the early iron projects. And then, of course, the next interface that arose was the computer. And I like to go back to the origins of things. And so this is Ivan Sutherland at MIT in 1962. And in 1962, he in one single thesis created the first object-oriented software, as well as the first touchscreen interface, including a stylus, where he was able to actually draw objects and create constraints that would kind of automatically solve themselves. This was in 1962 that happened. And then, of course, the computer morphed through time, and I think the computer both aids us and it limits us. You think about a hand-drawn line; it has difference of weight, difference of texture, difference of color and stroke, but the digital line is infinitely thin, right? It's mathematically precise, it's absolute. I run a sketching class for our engineers, and I put a piece of CLT on the table, and I tell them, draw that piece of CLT. And so then they pick up their pens and their papers, and you have 40 or 50 different drawings of that little CLT block. And then I put up on the screen the Bluebeam version of that sketch, and it's all red lines, and it looks the same. And so you lose that kind of human touch when you start to draw on a computer, almost by definition, because it kind of unifies and averages. And if we think about the computer and the next interface that's of course risen over the last 3-4 years is AI. And we talk about the computer making a drawn line average. Well, AI may make your entire building stock completely average, because that is what AI is. It's a large language models at the end of the day are general purpose transformers, and they basically give you the average best result. That is how they work. And so I think now we have this vast knowledge at our fingertips, but with this incredible power comes an incredible responsibility. So I think we as designers need to be careful of not passively accepting the machine's optimizations without understanding the first principles that guide them and are behind them. So I think over the next 10 years, we're going to see an entire new realm of software emerge, because we're going to have tools that are smarter than anyone ever would have imagined. And the question is, what are we going to do with those tools, and how are we going to shape them? Because how those tools emerge is going to impact actually what we design into the future. Because I firmly believe these interfaces actually influence what we design. And of course, it's not always true, but you look at the majority of building stock, and yes, it becomes easy to pick out of a catalog or easy to create a box. And I also think about the fact that humans, designers and builders, they used to spend 10 to 20 years on a project. And now, we have 1 to 2 years for each of us on any given project, and we're working on 10 projects at once or 20 projects at once, right? And the way that the construction and design industry has moved, we've actually kind of erected a wall between design and construction. I call it the construction contract. And we lob change orders and RFIs over that wall at each other, right? And this wall becomes more of a divider than a bringing together. And so, I'm a firm believer that we need to reconnect design through to manufacture through to construction. And that has to happen throughout our industry in order for us to get back to being able to build the Empire State Building in 13 months or whatever it was. So today I'm going to talk to you a little bit about shaping raw materials using timber. And hands up in the audience, does anyone know what a peeler core is? One person knows what a peeler core. Okay, so you take a log and you break it down into pieces of wood. Typically, we see them as rectangular pieces, right? And we see glulam made out of rectangular, we see lumber, CLT, etc. But actually, plywood, the manufacture of plywood, involves taking logs and peeling them. And so after they've been peeled into these layers, these layers get kind of glued up into plywood, but you end up with the very center of the log, which is basically most juvenile wood in the tree. And it's young wood, it's not very strong, it's very susceptible to checking, it's unreliable, it's quite statistically, it's not very reliable, got a high degree of variability. But there's a lot of them. There's actually billions of these things worldwide, and they're either chopped up and made into basically pulp and paper, or they're fence posts, or not even, they just end up in landfill. And so this was an early project that my father did about the year 2000. And this is the idea of taking these waste material peeler cores and turning them into a tetrahedral space truss. But in a normal consulting engineering role where you have no control over construction and over the build, how on earth do you get something like that to even exist? Well, how are you going to convince the general contractor? How are you going to convince the owner? Where are you going to source the material? How are you going to understand how much capacity these peeler cores actually have? And so his approach was, I'm going to go buy a bunch of these myself. I'm going to get a professor at the local university to go test them, and then I'm going to invent some connection to restrain the checking and the kind of problems that we have at the ends of these types of peeler cores, and then take on the risk of actually building the structure as the designer. And so by doing that, all of a sudden you can go realize the structure, and you can say, hey, to the client, I'm going to give you a fixed price for delivering and building this structure. And so here you see some of the details for how that space truss was created. And it is a highly variable material. You can see the giant checks in the truss, but it's still standing nearly 30 years later, and a really neat structure. The next way of shaping raw wood, this is the 2x4, the ubiquitous American unit of lumber, right? And this concept was almost taking lumber and arranging it into these V-shaped panels to create a highly efficient structural form. So normally a 2x4, you might be able to span 3 meters with a 2x4. It's about 90 millimeters thick. But here, by arranging it into the shape of a V, not only do you create the structural efficiency of the depth, but you also have this ability of actually integrating acoustics into the panel. So only every second lamination is continuous. And so then there's these gaps that form that actually absorb the sound waves. And so on this project, we're actually figuring out how to manufacture those panels ourselves and how to actually create the machinery to go build these prefabricated panels and a hydraulic press to go bend it into shape, etc. And then we're actually doing our own load testing. And so this is full-scale structural load testing. How does this panel behave? Well, we don't know. Is our SAP 2000 model accurate enough? Maybe not. Maybe not. But let's go test it. Let's go test 12 of them and actually truly understand how the structure works, and then get happy with it, right? And so truly understanding how the structure performs. So here's these panels getting installed. This is for the speed skating oval for the 2010 Winter Olympics. And moving on from that, taking this curved lumber maybe one step farther and curving it into curved glulam. This is in China. This is a series of domes with Deluge and Meisel architects out of Vienna. And these domes were three different biodomes. And so you've got a desert dome, an aquatic dome, and et cetera. And these domes were kind of ideated as almost like a clamshell type of geometry. So they're not spheres, they're actually quite complex geometrically. But we had some different constraints, and we're starting to allow these manufacturing construction constraints to actually inform the structural concepts that we're coming up with. So here we came up with this concept of a prefabricated panel, but the size of it and how it's made is governed by, hey, we got to fit all this material into a shipping container. And hey, we want doubly curved glass, but we want to limit ourselves to what's cheaply available in China for doubly curved glass. And so that those constraints started to influence the structural system and how that was ideated. And so here you see this glulam, which is actually some of it's singly curved, some of it's doubly curved, and it's actually CNC milled to create the second curvature. But it's creating these prefabricated panels, which we actually are able to quality control off of the job site and then fly into place on the structure. This is kind of almost like a shell structure with either 2 or 3 layers. And so this is quite a unique structure from an engineering standpoint, because it's you can't weld, like the British Museum or Smithsonian, you got these steel grid shells which are welded, and with the welding we get in-plane shear stiffness from a structural perspective. Well, with timber you can't weld, and so you have this phenomenon we call in-plane shear buckling of the dome. And so to restrain against that, we actually came up with this kind of diagrid of cables only on the largest dome. And these cables are kind of running across the underside of the shell, and they're connected to this casting. And we had to come up with this concept for how are we going to tension this cable net. While I was here in London at Bura Happel, I got the chance to work on the Olympic Stadium here, and I got to go out in site and watch them, using these giant strand jacks to induce tension into the cable nets. But here, if we were to do that, these cables are connecting at like 40 or 50 nodes along the place, and so we would have just ripped them out of the timber shell if we tried to yank at one end to induce tension. And so what we actually did is we came up with this concept of a threaded rod, which goes through the body of the casting and then has a nut at the back side. And that nut actually spins and drags the entire cable net closer to the grid shell. And by doing that, we've actually lengthened the cables and thereby induced pre-stress into the castings, into the cable net. So here you see that casting, and everybody asks, was this bamboo scaffolding? No, it was not bamboo scaffolding. It just kind of looks like it in the picture. But here you start to see this shell take shape. And again, this is, I think, maybe one of the first projects where we were really starting to think about how to reduce the steel in our timber structures. And so the only connection between these 2 layers is actually screws, nothing other than screws between these 2 layers of timber grid shells on the smaller domes. On the larger domes, we had the cable net underneath as well. So taking that one step further, that idea of curved glulam, this is almost a hybrid structure in Chengdu in China as well. And this is a series of vaults for an agricultural expo. And here we're kind of exploring a hybrid structural system. So we're using timber cords to these trusses, but we're using steel webs to create this trussing and arching action. And so if you think about an arch, obviously, a catenary would be the most efficient arch. But when we started to think about trussing it out, well, actually now we could achieve some structural depth at the base, and actually then the bending moment diagram changes a little bit, and actually the efficient shape for this structure becomes something which is kind of fatter at the bases and a little more narrower up at the top. And then we're actually coming up with this concept, which you can kind of start to see the hint of here, which is using these steel webs, but not actually triangulating them. So we're actually not triangulating the structure. So and then we're using some optimization techniques to kind of figure out the efficient distribution. But the reason these steel webs are not triangulated is from a construction standpoint. So we want to be able to prefabricate. We had to build these vaults on top of other steel and concrete structures that were getting built underneath them. So it's a very tricky construction sequencing problem. And so we also had to build this thing during COVID, which was insane. We only managed to get 1 person into China during the entirety of the construction of this project. So what you're seeing here is our like 3D IKEA sequencing diagram. How do you go build this thing in like visceral detail? You do this, and this is how the jig looks, and here's how you're going to install the screws, and here's how we're going to prefabricate these steel webs and then splay them out and bolt them into place. And then here's how we're going to create this kind of almost set of prefabricated components, which are kind of manufactured at small sizes and then linked together into larger pieces that then get craned into place on the job site. And so this is again all about minimizing the number of picks and the amount of work that we would need to do in the air on the job site in China. And here's some of the pictures during construction. And we had to kind of quality control this with drones, because it's like, like we can't get up there, and nor can the workers, to be honest. And we need to know, like, did the connection get done correct? Especially in China, can we trust all these types of problems? The local design institute basically just handed it over to us. It's like, well, we don't know. You figure it out. And so we were both the engineers of record and the basically responsible for the procurement of the material and the construction sequencing, et cetera, on the job site. And so this is Asia's largest timber structure. So this is 75,000 square meters. It's a huge, huge structure. And it was installed in around 8 months, which is also mind-boggling. So I think we had up to 13 or 14 different cranes going at once on the structure. So pretty incredible. But here, the one of the unfortunate things on this project is we weren't in control of the envelope. And we specify, you might have seen, the timber is kind of exposed. We specified nice flashing details that they refused to install. So we're still kind of dealing with the outfall of that. So when you're working in China, you don't always get to control everything like you might if you're working other places. So continuing on the theme of the 2x4, this is a project. It's actually an aerospace museum where we're kind of bending the 2x4, but as a panel. So imagine taking a flat mass timber panel and bending it into shape and then pre-stressing it against basically steel wires. And so by doing that, by pre-stressing it, we're creating a mass timber panel that can clear span 18 meters. So it's 90 millimeters thick and it's spanning 18 meters. But we're doing that with these kind of pre-stressed kind of cables. So we're adding a bit of steel, but we're creating much more materially efficient structure. Here we are in our manufacturing facility, kind of testing out the bending for the first time of these mass timber panels, and then out on site, stringing up the prefabricated trusses to crane them into place, creating this almost rhythm of timber and steel trusses. Also wanted to talk about kind of using timber in taller buildings. So this is a residential building with Michael Green architecture, where we're challenging, can we use timber cores in high seismic zones? So this is in Vancouver, which is a fairly high seismic zone. And here we're actually taking CLT wall panels and we're linking them together with steel link beams. And these steel link beams actually allow us to create almost a ductile fuse, so that in the event of an earthquake, these fuses actually yield and dissipate energy as the building rocks back and forth. And this is some PhD research from some of our engineers actually at the University of Canterbury in New Zealand, where we're actually kind of figuring out the hysteresis loops, for those of you who know seismic design, basically the energy dissipation loops for these steel link beams as you kind of yield them back and forth. And so this building, if it gets built, we're going to see. But if it gets built, it's going to be the tallest all-wood building in a seismic zone, I think, anywhere in the world. So it's a 12-story building. So that'll be cool. And this is my current favorite project, which is we affectionately call it the Pringle. And I got sent a photo from the job site after we just finished landing it about a week and a half ago. So you guys are going to see some brand new pictures and videos. And I got a picture of one of my guys with like a big giant Pringle, and them going like this, in front of the structure. And the bag of the little Pringle container as well. So this is for FIFA. It's like a band shell for World Cup viewings, and so this is a really interesting structure from a few points of view. The actual geometry of the structure, we're using this middle one here, which is a surface of constant negative Gaussian curvature. And I don't expect all of you guys to know what that means, but it basically means the surface has some very unique geometric properties, which actually allow us to create a grid on the surface, which actually does what you're about to see here. If it works, maybe not. Try that. Okay, here we go. Which does that. So it's like a rectilinear grid of elements. It's kind of like picking up with some of the things that Frey Otto and did at the Mannheim Multihalle, and of course the Wilden Downland and Savile Gardens that so many of Biro Happold worked on. But taking that and we're actually turning it into something that we're actually interested in using the structural system kind of repeatedly and turning it into something that we can actually prefabricate and almost crane into place. And so this lath grid shell actually gets draped onto this kind of doubly curved glulam ring beam. We had some fun doing some wind tunnel versus CFD on this. That was pretty interesting. As an engineer, I always wondered, like, can I trust the CFD or not? And so this was my little I get to nerd out moment, and we got to go do a wind tunnel and do the CFD and compare. And sure enough, the CFD is not quite there. So we had to use the wind tunnel results. That was pretty interesting though. And here we are in our manufacturing facility, actually testing out the constructability of this grid shell. And so this is like mock crane day, right? And so we've got the guy who's actually going to go build the structure. He's on the end of this mini crane, and he's figuring out, well, how is it going to actually fit, and where are the stress points going to be? And so this was pretty fun, just building models. This is a 1 to 10 scale model, and so building models that are not just models to look at, but models to actually test and understand structural behavior. And so these laths are about 70 by 70 millimeters, and they're connected by a single bolt. And so that single bolt kind of allows them to move and allows that kind of those rectangles to become diamonds, as it were, as this thing morphs into shape on top of the ring beam. And doubly curved glulam for the ring beam is something not really available in North America. So we actually went and figured out how to make that ourselves. So we built giant jigs to go press these huge bananas and create the glulam. And so here you see it in our facility. This was actually probably the hardest learning process on the entire job, figuring out how to actually manufacture doubly curved glulam that actually meets the structural requirements and certification requirements. That was quite the challenge. So here's the beams, and here it is coming into shape on the job site, and just a drone view looking down at this kind of laths pre-built offsite, and then the ring beam ready to kind of receive it. And I was out there, I think almost exactly 2 weeks ago. And I went out there for the test lifts, not the real lift. I went out there for the pre-lift to make sure it was actually going to go okay, right? And then the neatest thing is you can literally come up to I went up to that corner of this thing and just grabbed it. You can move it up and down by like 6 feet just with your bare hands, because it's so flexible. It's almost like a sheet of timber hanging there in the sky. So that was really cool. But the most tricky thing here was actually the rigging design and figuring out how to rig that so that as it comes and drapes down, you're not inducing undue stress into the laths as it's kind of self-forming into this shape. So that was pretty fun. But these are, I think, very efficient, material efficient shells, because this is about a probably 25, 30 meter clear span. And we're doing that with 70 by 70 timber laths. So lots of fun on crane day, and I got to be on the end of one of the taglines as we're kind of like guiding this thing into place. So that was pretty fun. But yeah, it's fun when you're building your own structures. You have like more of an emotional attachment to them, and you're actually like, I care about the details. No, that has to be right, and you get to take a higher level of ownership over your buildings. Just go through some of the pictures of the kind of starting to see the pattern of the shell. So now I want to talk about kind of this return to timber joinery I hinted at earlier. I think, if we think back to the birth of every structural material, let's call it rebirth, modern rebirth over the last 150 years. Think about iron and Brunel and the magic he did with wrought iron. And then you think about Candela and Eisler and Nervi and the incredible work with shells, or Dieste with brick. Or Frey Otto with tension and timber, both. In the early ages of each of these materials, there was a lot of innovation. People thought outside the box. They weren't limited by a catalog. They weren't limited by the wide flange section size with the shear tabs and 3 bolts, right? They could invent because the materials hadn't yet been codified into your, I don't know what the color of the book is here, but the red book, right, of steel details. And so with timber, we're kind of at that point right now. Is people are just starting to relearn how to design and build with timber. And so I'm very interested in kind of challenging what I started to see as the status quo in mass timber buildings around the world, where we connect timber pieces together with giant steel monstrosities, hundreds of pound steel connectors, bolts and dowels and screws all over the place. And if you look at ancient timber joinery, well, there was none of that. First off, it didn't even exist. But they found ways. There was inventive ways. You look at historic joinery in Japan or in France or in Germany or in China, of course, incredible ways of doing and connecting timber. And so I'm just going to show you a couple of projects where we're investigating ways of creating projects with timber that use no metal in the joints. So this first project is the New School of Architecture at the University of Kansas with Bjarke Ingels' group. And on this project, he was kind of challenging the design team to think beyond typical building design. You want to challenge the next generation of architects and designers coming through this building to think differently about how we conceive of buildings. And so this structure is actually a diagrid. So it's like a timber exoskeleton. It's a 6-story building. But the lateral loads are actually all taken in the exterior. And so the central core is non-structural effectively. And so in this building, we're actually kind of exposing all the surfaces. We're attempting to remove all drywall from the building, no drywall. And we're using kind of mineral, like some really interesting mineral wool or hemp in the envelope to kind of deal with thermal. And so for me as a structural engineer, the biggest challenge was, okay, so we have this diagrid. Well, how are we going to connect the timber elements together? And so here I was on a call with Bjarke early in the project, and I asked him, so like, how do you want to connect the joints? Do you want to expose them? Do you want them to all just disappear? And then he started sketching, and then he was like, well, how do you want to connect the joints? So I had to go start thinking about, well, what did I want to do as an engineer? And of course, you have this, we call it the hero node, where you have like this 6 stories of structure coming and transferring out to these 2 diagonal columns. And we're starting to think about like, how should we do these joints? Should the timber columns be continuous or break? And I started sketching some of the steel details that would be required, because of course my mind goes immediately to using metal. And I was drawing all these plates, and I was like, oh, there's going to be so much steel in this structure because the loads are pretty high. And then I was like, well, what if we like just flip the script, and what if we said no steel at all? No steel allowed. And so this was the next page in my sketchbook, where I started sketching kind of this idea of using almost sawtooth joinery to connect the timber elements together and just actually do that through geometry rather than through some sort of metal connector or screw or dowel. And so this is us down in our workshop about 6 or 8 weeks later, doing a prototype, like a 50% scale prototype of that joint, and then kind of starting to see, is it going to fit? And can we do it? And what about the tolerances and shrinkage, et cetera? And so we actually got the opportunity to build a full-scale mock-up of one corner of the building. And so this animation will kind of show you how, like, if you peel back the structure, which actually you can't really see the joinery when you look at it, but if you peel it back, well, how does that actually happen? And so this is kind of, there's a timber dowel, and then there's some little basically glorified plywood pieces, which kind of create a shear key between the elements. And then we're starting to use this kind of big sawtoothing to actually allow us to kind of take these braces and transfer the load in parallel and perpendicular to grain compression between the joints. So a lot of fun kind of exploring that even from a 3D perspective, but also starting to think about how do we do it on a scale. So this is the full scale mock-up. And then, how are we going to mill these? And are we going to put these on our CNC machine? Is the CNC machine accurate enough? And our master carpenters came to me and said, we ain't using the CNC machine for this one. Let us at it. We want to do this. And so we actually ended up using the CNC machine to kind of take it down most of the way, but then the finishing touches were actually done by hand. And so that kind of craft came back into it to kind of achieve the level of joinery and kind of tight fit that we're envisioning with the structure. So that was fun. And the next project that we had the opportunity to kind of think about wood joinery was actually for a performing arts center in Barbados. This is with Ajay Associates, and this is the new National Performing Arts Center. And we got given kind of like an impossible task. In about April of last year, they released us to start design and construction on a structure which needed to be built by August of the same year. And as you can imagine, that's just an impossible timeline, right? And initially I was like, we're just going to turn it down. It's absolutely impossible. And then, I started thinking, well, hey, actually, maybe it is possible. And, yeah, it's going to be a crazy amount of work, but maybe we can find a way. And so we actually took the structure and we kind of de-scoped it down to this almost central pavilion. So, you can't build the whole structure, but okay, maybe you can build an initial part of it, right? And so this is kind of starting to sketch, okay, we have this big truss which goes across the main stage. And for that big truss, this is starting to sketch what the concepts were. And when we're coming up with concepts, because we have carpenters and people who are running our CNC machines, we can bring people to the table as we're ideating these connections that normally just as a pure engineer or as a pure architect, you wouldn't have access to, right? And so we're starting the idea I came up with was almost this compression truss, because with timber, you can easily transfer loads and compression. Tension's much more difficult if you're trying to do timber to timber joinery. So we basically creating a diagonal arrangement, which is prioritizing compression. And this truss, which is clear spanning 80 feet, so that would be, yeah, it's 20 some odd meters. This truss, so if you just did two beams, well, you got big bending loads, right? If you truss it out, it's great, but then you have all these big tension loads, but you can start to see almost like a proscenium arch emerge, right? And so this arching action in the form of a truss is really kind of what we're going for. And this is, okay, yeah, you just run your algorithms and figure out what the optimal thing is. And a lot of our engineers love to do this, but the interesting thing is you do that and the theoretically optimal design and geometry, well, it doesn't actually work, because it doesn't think about the connections, it doesn't think about splices and constructability and how the connections work. So, you end up actually having to go change a little bit away from the theoretically optimal to let's call it real manufacturing optimal from a design perspective. And so this is kind of that truss in a render. And then this is some of the initial kind of sketches looking at, okay, how do we splice these pieces if they're 80 feet long and we can't ship them that long from Vancouver to Barbados? They have to be spliced. So then we're gonna have to do a moment splice, we're gonna have to do a tension splice. And so this is kind of just starting to sketch through what those joints might be. And what might those joints be if we actually just from the start said they can't have any steel? That's a fundamental assumption. There is no steel in the structure. Okay, well, what is that going to do? And what kind of geometries might we imagine if that is the kind of predicate? So here, this is kind of like the bones of this kind of canopy or temporary kind of pavilion. And it's not, by the way, this pavilion is actually going to be part of the finished structure. So it's not like a throwaway pavilion. This is like actually a part of the building. So we kind of just build it out one more time. But here now you're starting to see kind of all the different joints that we're doing. So this is a big tension splice. This is taking about 150,000 pounds of tension. And these ones are kind of more lightly loaded splices that are, again, just kind of tooled into the bottom. And of course, we have to oversize the structural elements a little bit to make the wood joints happen. So you end up using a bit more wood. But in this case, I think it was worth it, because one of the things I'm not saying that we should all use all wood joinery all the time, but by doing some of this, what I'm hoping to do is inspire people to question, why are we using so much metal, or why are we using so much material? And so here we are in our shop, chiseling out the material. These beams were too big to fit in our CNC, and to be honest, we didn't have enough time to CNC, because you only have 1 or 2 CNC machines, and you need to be working on many things at once if you're trying to design and build a structure inside of 4 months. And so here you see some of the master carpenters at work, kind of figuring out the joinery. And this is literally probably 5 weeks after my sketches that I showed you earlier. Can you imagine? We bought the glulam before we had even fully designed the connections. So then the glulam hits the shop, and then you're into manufacture and production. And so this is a picture of the whole team inside the truss, the whole team that went manufacture that. So this is the test fit. And then, of course, shipping it to site, we had chartered 2 cargo jets to fly it from Vancouver to Barbados, because of the timeline was just so tight. And then it turns out, guess what? The airport in Bridgetown cannot unload a 747 cargo jets, because their scissor lifts don't go tall enough to reach the deck of the cargo jet. And so I was like, oh man, okay, we're not going to make it. We tried, but yeah, game over. And then we had this idea of like, why don't we actually charter a boat? So we chartered an entire boat and we trucked the material from Vancouver to Houston, Texas, and then from Houston, a direct boat to Barbados. So it was like we probably had it like 10% full, but it didn't have to stop anywhere. So only took, I don't know, I can't remember, a few days to get there. So here's our, and one of the other incredible things is one of the guys you saw in that picture of us sketching ideas worked not only in the 3D modeling, but also out in the shop on the carpentry. And then he went out to Barbados to help actually build the thing. So you have this somebody who's involved literally right from kind of concept to construction of the built structure. So here you see this was a scary moment, kind of lifting this all wood truss and putting it into place, and how's it going to go, and what's the deflection going to be versus what you predicted, and all this type of stuff. But it came together well, and let's get through some of this. And we actually managed to get the timber to the job site before they had even finished the concrete, which was quite something. And the reason this was on such a tight timeline was this is for Carafesta, which is the Caribbean annual festival. And the Prime Minister of Barbados wanted to host the opening and closing ceremonies in this pavilion, kind of launching it as the new Performing Arts Center for Barbados. So that was pretty cool. And so we kind of just in the skin of time finished it. And so yeah, started design to construction in 4 months on this, which was pretty. You can't do this if you're not integrated. It's just impossible. And the reason I like to show this is because it calls into question, well, why are we doing it why are we doing it this way these days? Why aren't we more vertically integrated as an industry? And finally, I'm just going to quickly talk about our software ventures. About 5 years ago, I've always been interested in software and programming as a person. And 5 years ago, I had the opportunity to start something inside our company we're calling Branch, which is kind of new software I'm envisioning for our engineering and kind of manufacturing industry, because we went and measured our digital footprint, and it's kind of like ginormous. 30 different pieces of software to actually get from conceptual design all the way through into manufacturing. Really? Like, is that what we would have created if we were starting brand new and the computer was a new invention today? Would we have created 30 pieces of software to do what we do? No, right? And so, we're on a mission with Branch to almost create a new piece of software which allows us to go from manufacturing. So this is Branch, kind of an early version of Branch working inside of Rhino and doing all of our manufacturing detailing. So it's doing our LOD 400, 450 detailing. And it's going all the way from the detailing through into the shop drawings, through into our CAM software to run CNC machines. And not just ours, we're working with manufacturers all over the world. So we're using Branch to actually produce drawings that drive manufacturing. And so 3 years after that, so that was, 3 years, like we started in about 2021, but by 2024, we had done thousands of shop drawings. We had built about 2 million square feet of buildings using Branch. And so we actually kicked out Tekla or CADWork or HSB or these other detailing packages, and we only use Branch to do our detailing. And this is just like a sneak peeks, flash through of all the different shop drawings that have been generated in Branch over the last 3 years or so. So all sorts of different timber and steel pieces, ending with the shop drawings for some of the pieces I showed on the truss in Barbados. And so we started kind of with this idea of making detailing software because I wanted to see, could we actually go build our own piece of software that could do anything meaningful? So we kind of succeeded at that, and now we're starting to look at kind of conceptual design. One of my pet peeves is our finite element software as engineers is just so slow. Click a button, wait minutes. It's a disaster. Right? It shouldn't be that way. Our computers are definitely fast enough. So what if we went and built a piece of software that would allow us to analyze our buildings in milliseconds? And so as you push and pull, what you're seeing here right now is as this person is editing the massing of their building, it's actually in real time analyzing and sizing every single piece of structure in that building. So every beam, every column, every panel is actually getting live sized. And so what that means is you can go investigate your different grid sizes or your grid spacings. You can go see what the impact is on carbon or what the impact is on your material quantities or your quantity takeoffs. And now all of a sudden you can go study options, because I think often we don't study options because it's like, well, man, I've only got time to do one Bluebeam sketch of maybe 3 options for you, Mr. Architect. Sorry, that's all I got time for. But if you could kind of go and investigate it more more rapidly. The other reason I'm kind of obsessing on real-time feedback is because the human brain is incredible. We can take in feedback at a way better than 60 frames per second rate, right? And yet we're sitting there and we got to go grab a tea because we're waiting for our model to run. Well, I mean, that doesn't encourage creativity, doesn't encourage studying options. It doesn't encourage understanding your structure either, because you don't have immediate haptic feedback when you're using the software. And so this idea is kind of like that we could really, change your spans or change your grids or change your material from concrete to steel to timber and understand the actual impacts on your building structure at a very early stage as you're changing these things, and truly kind of start to explore more options and make better informed decisions, more efficient decisions. Yeah, I know I'm still showing only rectangular buildings here. And I just finished earlier saying that we need to reintroduce curves for efficiency, but we'll get there. And so just to finish talking about AI, I think AI could start limiting us as designers. We could be delegating the work even more, removing ourselves even further from direct interface with our building structures. But I think better way of thinking about it perhaps is that AI is going to be like a toolsmith. It's going to create tools that we control. And that's one of the reasons I'm building branches. I think it's very important how and who builds the next generation of structural design software. It should not be click a button and design my building. It should be an educational tool, because I think about how am I educating the next generation of engineers who are going to grow up in a world where it's like, oh, you need to design a wide flange beam? Well, I just typed it into ChatGPT. And I have no idea how to actually do the calculation myself, or even all the constraints and the different things that impact that particular calculation. And so, I think it's not AI doing the thing, it's AI making tools that help us do things. And I think they're incredibly good at that. And so, I do this kind of like scribble. It's like, for those of you who are structural engineers, like none of us trust AI, right? Like nobody is like, I'm going to go ask ChatGPT to design my beam. But there are generations of engineers coming over the next 20 years who will trust the AI. And the senior engineers, who many of you are going to become over the next 15 years, are going to be like, you can't trust it, right? And so then, well, what are we going to do about it? So what I'm thinking is actually we need to start using AI to reason about deterministically correct things. In other words, it's not possible for the AI to do anything but reason about correct components. So imagine if it's, instead of doing its own reasoning, it's actually stringing together components of like calculating structural elements or connection design or whatever that have been human verified and are verifiably correct. Well, now we could start to maybe trust what it's doing as a system. And so this is inside branch, just more of a thought experiment more than real functionality. But imagine if you had a structure kind of this complicated and you wanted to start understanding how your building behaves and what might AI functionality look like. Well, maybe it looks more like I'm telling it what I want to do. And instead of it doing it, it's actually creating a tool, and it's starting to live create tools that can allow me to better understand my structure. And so now I have this column inspection mode because I said I wanted to understand my column behavior. And that's a custom created tool that I just created for me with AI live in the app, right? Or I want to understand how the forces flow in let's call it the force graph of the structure. Or I want to understand the bending or the shear diagrams on my beams. And so I think AI is going to definitely change what software looks like over the next 20 years, completely and utterly. But it's very important for me, like, that it's becoming more of a teaching tool. And actually, it's making software better, because think finite element analysis, we ended up creating software that all it does is analyze buildings. It doesn't actually teach you anything about design or even about what to look for when you're doing finite element analysis or whatever other structural design method you might be doing. So yeah, with that, I want to just close and encourage everybody here to take joy in the details and master, of course, all these digital interfaces we have in front of us, but don't lose the connection to the material or lose the connection to actually building. Get out on your job sites, understand the contractors and what they go through and how they actually build the structures that you're ideating. So with that, I'm gonna close. Thank you all.